Thanks, Rob, and good morning to everybody. Fantastic to see people not on a team screen. That's great, isn't it? Let's see if we can work this out. We're going to go down, aren't we? Okay. So I'm going to talk today a little bit about a project we've been working on and its wider context to alternative methods to electric vehicle charging, and how this project Escape is helping deliver those solutions, and particularly in respect to silicon carbide technology. So it's first time AESIN for TPS, so probably worth me just explaining who we are. We've been around about 40 years. We very much got a pedigree in the rail sector. We started all that caper in the 1980s. We still do it, but we make lots of equipment for rail. And we also make equipment for the aerospace industry, particularly here. If you're on a Boeing 787 and you happen to be having an emergency landing, it's our equipment that's going to get the fuel off the aircraft for you. Going into the noughties, we entered into the industrial market, high-speed electrical machines, power electronics to drive them, particular sectors like HVAC, water aeration, separation. Going into the 20s, we're getting interested in energy, particularly how we're going to solve the problem around the grid as we electrify everything around us pretty much. And it's a very interesting problem. At this stage of the presentation, you're probably thinking, well, what's this clown doing at an automotive conference? Well, I want to touch on something that affects potentially all of our aspirations in this room today. So it's the power challenge. It's estimated we need another 13 to 20 gigawatts of additional capacity to meet the needs of our electric vehicle forecast, and we need it quite quickly. It's not a supply problem. We're getting really good at being energy efficient, so don't worry about where that's coming from. The problem is about localized constraints on the LV distribution network. And the problem presents itself as a £50 billion problem that the DNOs, via yourselves, the good taxpayer, are going to have to solve. Okay, and this is going to involve, if we do it the traditional way, replacing cables in the ground, substations, and it's not a simple problem, particularly when you add to the powder cake the need for electrified heat. I've worked in engineering nearly 25 years. I've never seen a silver bullet to a big problem. Okay, they don't exist. People say they do, they don't exist. It's all about diversity of solution, complementary technologies. So how are we going to solve this problem? So demand management, battery storage, it's all good stuff. It's likely to solve about 10% of the problem, but we need it. V2G has got a game to play, vehicle to grid. We can create some capacity with all these mobile generators that we're going to have. Need to incentivize people to discharge their batteries. We will need some traditional reinforcement. There are times it will be more economically viable. But we've got a couple more things we can put in the toolkit. So what about creating some local DC capacity? That's something we can do, and we're going to talk about how we can do that. And if this problem's at the LV level, why don't we try and access the MV level? More capacity there. So I'm going to get quite technical with this slide. It's quite an important background, but here's our grid today. It's a very simple network. It's a cascade of voltages coming down from 132 kV to 400 volts. Electricity travels north to south, and that's it. That's your lot. Okay? Now, moving forward, we've got to make electricity do clever things. So we can start off putting what we call soft open points in the network. Soft open points can connect different feeders together, and they allow us to exchange electricity east to west or west to east. Why do I want to do that? I might have one overloaded feeder, and I might need to relieve that feeder by introducing some capacity from a feeder that's underloaded. The beauty of doing a soft open point is that we have a DC bus, so we can connect vehicles to the DC bus. We can replicate that game at the medium voltage level. Again, we can add electric vehicle technology, charging. Solid state transformers. Now there's the technology, that's going to happen at some point. These can help the AC network as it is, but they can also create DC networks because they have a center tap DC. On that, we can add a load of low carbon technologies. And you can keep going. What we're doing here, you can see we're creating levels of DC networks to complement the AC network. And you keep going until you end up at the high voltage intertie. You can tie the networks together You can even tie the DC buses together. And this is all happening in DNO world. They're looking at all these solutions. We can even tie the rail system to these DC bus. And this is great. DNOs are all looking into this. But what can we do privately? Okay, we can take these similar approaches, or we could address fleet charges. Fleets are going to have a massive demand for electricity. So at LV, we can create a local DC network. We can put storage on it. We can put vehicles on it. We can put solar PV on it. We can do it at the MV level as well. And what's interesting about all of this, you note my somewhat cheesy title to this slide, but you know, we're dealing with DC technologies, EVs, solar PV, fuel pumps, everything's DC. So why do we want to keep going DC, AC, AC, DC? Well, let's keep it DC and be a little bit smarter and a bit more efficient. And this enables it to do this. So I'm talking about smart fleet. The charger you see outside is part of this solution. Here's the LV fleet solution. We put a grid-tied converter or a soft open point converter connected to the grid. It creates an 800 volt DC bus. We can charge from the electric vehicles there. We can do that at MV. The difference being we don't need a grid-tied inverter now. We need something akin to a solid-state transformer, which drops the voltage threshold. Or we can use a straightforward transformer rectifier. Key messages here are we want a flexible grid connection north of the DC bus, and below the DC bus we want common modules and scalability. So what I'm going to focus on here is that DC microgrid element, and then I'm going to talk about how we do the MV connect. Now, why even do this? What's the point? What's the point of creating these microgrids? Okay, well, it creates that capacity locally, and in doing that, we can avoid ourselves a big grid upgrade cost, potentially. You know, these are significant costs when we want to add capacity to the LV network. It can reduce the fleet operator's costs. You know, they have now the ability to arbitrage energy, store it use it when it's expensive, ship it to the grid when it might be good value to them. And we can do that with either AC microgrids or DC microgrids. So why particularly do we want to look at DC microgrids? Well, we can kid the DNO to some reason. If you want 1 megawatt of charger, we can connect all of those to the grid with a 400 kilowatt grid-tied inverter. And as far as the DNO is concerned, that's 400 kilowatt of charging power, but I've got 1 megawatt of charger. So through natural diversity of charge state and potentially a bit of addition of battery storage or solar PV, if you like, you are creating that capacity locally and potentially avoiding that big upgrade cost. And I mentioned earlier about keeping things in the DC world. Here's a use case of why it's useful to keep things in the DC world. I generate some solar power, I put it in the battery to use later. I take it out of the battery, I charge an electric vehicle, and I've got losses of 12%. If I do that on a DC network, I get rid of all that DC to AC, AC to DC, and I've just got my DC-DC losses, and they're about 6%. So I can save myself 6% energy going to a DC microgrid. In that particular use case, there are other use cases, obviously. So let's bring in ESCAPE. ESCAPE, end-to-end supply chain development for automotive power electronics. This is an APC-backed project because it's strategically quite critical to get a SiC capability in the UK. It's got 12 partners developing everything from wafer processing capability up to end usage application, which is where TPS sit. What it's helping TPS to deliver as part of the MV and LV fleet solution is some core components. So that bit below the 800 volt line I talked about, we need a DC-DC converter. It's a resonant converter, it needs to be compact, have a high frequency transformer in it for isolation, and silicon carbide's helping us do that for both 400 volt and 800 volt charging. It's enabling us to deliver the chargers. You've seen what we call the integrated charger outside. That's where this DC-DC converter lives inside. But for fleet, they might want to minimise the forecourt usage that they take. So we'll also be developing what we call a slimline charger, where the DC converters live in a centralised location and the charge point is simply a post. The really clever stuff comes with that MV fleet. We need that solid-state transformer. Unfortunately, we're not advanced enough for me to show you a nice graphic, but fundamentally this is what it looks like, or the general principle of creating a solid-state transformer. And we want to use that silicon carbide technology to do that. It's quite a critical enabler. So here is MV fleet. Here's what we talked about, the solid state transformer feeding the chargers. It starts to get quite complicated. Solid state transformers are complicated by their very nature, and we have 3 strings of converters. The direct current transformer is the clever bit. That basically takes DC, converts it to high frequency AC, and then converts that high frequency AC across a transformer back to DC that we can use. And those sections are comprised of lots of strings, and the escape technology is really helping us develop the MV to LV cell within that string, okay? And for this solution, there's 36 of them. We are bound to use 1200 volt devices, and Dave after me is going to talk a little bit about going to higher voltage devices, which can really help the viability of solid state transformers. Here's the MV to LV module. Here's the critical bit. Now, we developed a module here that fits roughly in a shoebox. It's quite small. It needs to be compact. It's 15 kilowatts. It's 98.7% efficient. The magic number is 99%, and there is a route map to that. The high-frequency transformer can now switch at 230 kilohertz. That's what silicon carbide does for us. So it's got a very unique transformer in it to enable us to switch at those frequencies. And we've got 12 modules per string, giving us N-1 redundancy. And using that, we can get to a 500 kilowatt solid-state transformer. But we don't want to stop there. Escape wants to deliver us a twin device. Okay, twin device silicon carbide processed in the UK, made in the UK. With a lower RDS on, we're targeting a half. Now, if we can get that lower RDS on, there's our 99% holy grail efficiency, which makes solid-state transformers work. Here's the flexible fleet solution. So I've talked about MV and LV. Here's how we do it. This is an example where we're using the slimline charger. We've got LV, we've got a grid-tied inverter, which is something we developed on other projects, but we could use this solid-state transformer in the centralized container for our MV connection. We've got the chargers, the charging modules, DC-DCs, they're living in this particular iteration in the container. And it gives us a number of features. So we can go LV or MV grid. We've got the integrated or the slimline charger. We can do V2X capability. Very simply, across that DC bus, I can take power out of the vehicle, put it to the grid, put it to the battery, put it to a heat pump, whatever, but in the most efficient manner. So it gives a very good solution for V2X. And using the silicon carbide, it gives us the optimal efficiency for the solution. That's not the end of us, and Dave, I'm hoping this ties into Dave's presentation quite nicely, but Escape's is giving us this ability to have a silicon carbide capability in the UK. I've talked about the twin module. The other partners are going to get a very beefy 1200 volt module for onboard solutions, 600 amp capability. We've got this unique opportunity coming up where, if we can get 3.3, 6.6 kV devices, with that baseline capability in the silicon carbide supply chain, we can start to look at different markets, like the distribution solid-state transformer market. And what that 3.3 kV device will do for us, you saw the complexity of the MV-LV solution. It will reduce that from 36 modules to 15 if we want to retain an N-1 redundancy. So you can see silicon carbide embeds across this and other sectors. And so I've given you just an introduction there to Escape and what we're doing with EV charging. Thank you.